So hi everyone, my talk is about self-trapping and interfaces in active matter. Myself Raushan Kant. My advisors are A.K. Sood and Sri Ram Ramaswamy, and I'm collaborating with Harsh Soni and Rahul Gupta. So the idea behind, the motivation behind it, doing these experiments and simulation is to study the active-passive mixture, for example, living and dead bacteria. And previously reported, Nitin has already shown that motile minority can mobilizes inert majority, where you can see this. How shall I? There is a list. Okay. Thank you. So the question is, can they drive other kind of organization? Okay. And the previous reports, the previous relevant reports in active-passive segregation is by core halo condensation by Steinhammer et al., where the core is occupied by the passive particles and the periphery of the this structure is occupied by the active particle. Whereas the Dulai et al. Have shown the condensation of passive particles driven by smaller active particles. And these particles do not possess any aligning interaction, whereas when these the McCandless et al. Have shown the lane formation when there is an active-passive rod mixture. Okay. So the experimental system is like this. The active polar particle is a brass rod whose size is 4.5 mm, confined within 1.2 mm geometry, and it is vibrated by permanent magnetic shaker. Here gamma is the shaking strength, which takes care of amplitude and frequency, and we vary that in order to vary the shaking strength. And the motility mechanism is when the under vibration, when these particles are tossed, they fall from the heavy side, and under the static friction, they move forward. Okay, so this is the experimental setup. So this work is about motile aligning rods and non-motile, non-aligning beads. We will present the results of experiments, simulations, and simple theory. Results are like, for a very small rod fraction, it goes from isotropic phase to flock to segregation. We'll also explain about the traveling segregated bands, and we'll explain that how alignment opposes a core halo in 2D, as well as a cell trapping. Okay, so in 2D, we see that we see a phase transition as a function of beat fraction, and we see that at 5b, at 0.55, we have a disordered state, and when we increase the 5b, we have flock, and then at 5b is equal to 0.77, we have a segregated phase, and this is happening at very small fraction of motile rods. Why the focus is okay? So the focus looks very. Can you just adjust the focus?
In resolution.
Okay. So sorry. So we are calling it. Just a minute. So we are calling it this segregated state, we are calling it interface state because the line decorated by these rods are separating two regions, which has different, like they are, one region is less mobile compared to other region, and they have different density. And one can see from the mean square displacement plot that region A is less mobile than region B. And these rods have always tendency to point towards the dense region. Okay, and we'll explain in the couple of slides how they are related to moving segregated phase. So in order to understand the effective one-dimensional behavior, we also carried out experiments in channel geometry, where we see that even at phi r is equal to 0.05, we saw a disordered phase, and then to flock to segregated phase, where I will two segregated phase where there is a self trapping. Okay, so so this cell trapping is like a core halo condensation reported by Stenhammer et al. And outside this core halo, we see the density of beads and rods are quite less, the question is that why we are not getting such core halo structure in 2 dimension. And in spite of these rods are tapered, they have a very strong, they favors parallel alignment. Okay, and because of that, it is not possible to form a splay configuration which can stabilize a circular dome made up of beads. Okay, in 2D. Whereas because of this, confined geometry, these rods are rod orientation is constant to azimuthal actually. So that's why in 2D, in channel geometry, we observe this self trap. Okay. So if you understand the kinetics of self trapping, starting from a random phase, we get a transient clock, and after that we get self trapping, and this capital P is the measure of order parameter of that, where it is defined as it is average over all rods, and this small pi is ni cross ri, where this ni is the direction of orientation of these rods, and the smaller ri is the position of these rods from the origin. So if we'll see the self-trapped state, like if for this side, if the capital smaller pi is in the positive z direction, for this side the smaller pi is in the negative z direction. So overall, if we'll sum over, if we'll average over all those rods, this is effectively 0. Okay. So this is the phase diagram in quasi 1D, and it is bead area fraction versus rod area fraction. If we take a vertical cut, we get disordered phase to ordered phase to self-trapping. And in 2D also, we get, if we take a vertical cut, you will observe disordered phase, then to flocking, and then clustering, and then interface state. So, and these are the snapshots of the corresponding points in phase diagram. Okay. So the results, the simulation is done by Rahul and Harsh, and this particular simulation is a square simulation box, and this is based on impulse-based collision model. They observed that there is a moving segregated phase, and behind these segregated phase, we see a trail of bead pore region. And this phase is essentially equal to this phase in the experiment, but because the experimental size is limited, we don't see a trail of bead pore region behind this in experiments actually. And we had already explained that why core halo is ruled out in 2D and why these aligning rod enforce flat interface. And the simulation done in channel geometry, we observed, from disordered state to ordered state to segregated phase, and you see this moving segregated phase where the steady state is the band of segregated rods. Okay. So in order to verify that, like we also did the simulation in this combined geometry, and we get self trapping in simulation as well. the sketch of this, the sketch of coarse-grained theory could be that we take rod density field and bead density field, and the velocity of beads is proportional to polar order parameter, and this aligning interaction of rods works in polarized state, and these rods orientation drives the bead motion, and there is a tendency of rods to point from a low to high bead density. As a result, we have a linear instability to bead rod segregation. So what we in summary, what we shown to you is the very small fraction of rods can drive segregation. We explained the interface state, traveling segregated band in 2D, self-trapping in quasi 1D. We shown phase diagram and how aligning interaction rules out the core halo condensation, and a sketch of coarse-grained theory which predicts segregation. Thank you.
So I had a question regarding, so you said that the rods have basically aligning interaction, right?
Yeah.
And these are essentially because they are cylindrical. So if you make the rods a bit more conical, won't they have a spray of this kind, and won't that lead to this kind of segregated phase in 2D also?
What you are saying, that if you make a rod
a bit conical instead of, so right now they are essentially a cylinder, right? So they would like to be parallel to each other, but if you have a conical rod, then they will have this type of an instability kind of a.
So in that case, they might form a curved structure, and in this case also there are few interfaces stated. They form bit curved structure, but it is not possible to get a circular domain made up of these rods which can stabilize the bead structure. That's what I am saying. Even if you make the rods bit conical. Okay.
If they're substantially conical, why would they not? They could. I mean, we don't know, but there's a good front back size difference.
Yeah. Yeah, that is, well, we have not done experiments. Yeah. So we'll have to see that. Yeah. Okay.
Right. So I was wondering that in the high density phase of the bead and all, like you varied the volume fraction quite a bit. So that bead density, when this self-tapping happens in the high density phase, is it always similar in all cases? Like suppose you start with different volume fraction.
Yeah.
You go to this trapped state.
Yeah.
And then if you look at the high density phase of the beads, so is it similar?
No, at high density, what will happen is these rods will, they have a very little space to move, right, in the channel geometry. So what happens is instantly, just after starting the experiment, they will jam. Some of the rods will just turn backward direction, and
I'm not talking about the rods.
Yeah.
In the high density phase of the bead.
Okay.
So can you like the position and what is the density of the bead?
Yeah, yeah.
In the high density phase.
Yeah.
So if you start with different configuration, let's say different volume fraction, area fraction to start with. Now, when the high density phase is formed, is it the volume fraction inside that high density phase is of the bead is always similar?
No. It's not always same. It varies, but one can study the hexatic order parameter to and we did that. The density is high, but there is they vary actually. It's not constant actually.
When you get high density domains, regardless of what the total area fraction was, regardless of what the total area fraction was, what Anton is asking is whether when you get a condensation into bead rich and bead poor, is the sort of typical area fraction in the bead rich regions roughly the same? There might be, it will be partitioned according to something like lever rule or something. But how dense the bead dense region is, I think is about the same. It will vary in time, of course, but I don't think you can get a kind of bead droplet which is not very dense versus a bead rich droplet which is very dense. I think it's self-regulating. It's more or less, it just gets pushed together, I think. Could be wrong. I'm assuming that's what you're asking.
Yeah.
Yeah.
Yeah, so
Yeah, so basically, when you succeed in condensing it, you more or less look at all the way. There'll be some range, but
that's what I was saying, that if you'll see, they will vary, but they will fall in the same ballpark, like 0.75, 0.73. That's what I wanted to say.
I think
Okay. Very interesting. Just I'm curious, so what happens if you just change the aspect ratio of the rods? Does that make any sense?
To be very frank, we have not studied that experiment. We have not done that experiments. But if you'll increase the aspect ratio of the rods, and the tapered, if you'll increase the tapered side, the length of the tapered side, the persistence of the particle will increase. So that's what I can say as of now.
Because earlier works of this Wenzik and this, they have also varied this aspect ratio, if I'm not wrong. So, and
I'm not able to hear you. Okay. Yeah.
okay, fine, we can discuss.
Okay.